In today's lesson, we're going to start into the last topic of the course, and that is the topic of regression modeling, or for this course, simple linear regression models. The idea with regression modeling is that we oftentimes have relationships between variables, and maybe we want to study that relationship. Maybe we want to understand how one variable impacts another variable, or predict one variable from another variable. Regression models provide us with a very powerful framework for doing this. And so in this course, we're just going to sort of start to look into what regression models are capable of. And I'll point out here that these topics go far deeper than what we'll get the chance to cover over the next couple of lectures, but hopefully it gives you a taste for what is possible with regression modeling. So in today's lesson, we are going to introduce the simple linear regression model and all of the components that make up the regression model. We also will understand the normality assumptions that go with the simple linear regression model. Right? So again, we have this normality assumption coming up. We'll talk about where it's necessary, where it's not necessary, and sort of why we use it. To motivate this, we can think about sort of any manufacturing process. So let's think about something with chemical engineering, and perhaps we're concerned with the yield, right? There's obviously a whole lot that goes into discussing the yield of a chemical reaction, right? And any number of those factors are going to sort of be controllable by us, right? So you could change the exact conditions for the experiment. You could change the exact reagents that you're using. Any of these sort of factors that you could change are going to have an influence on the yield. And if we want to try to understand that, then what we need is some sort of model that explains how the yield is impacted by all of these input components, right? There's obviously plenty of ways of doing this, but in terms of statistics, one of the most sort of common frameworks, one of the most powerful frameworks is going to be through the use of what are known as regression models, right? So that's what we'll be looking at today. In the last few lessons, we were looking at what happens if you want to compare differences between two different samples of data, right? So we looked at by-sample data, and then we were just comparing those samples. Oftentimes, that comparison will be useful, but perhaps even more frequently, we're going to want to know relationships. So not just is there a difference here, but how does one variable, how does one factor influence another variable or another factor? And whenever we want to consider these relationships, nothing that we've talked about so far is going to allow us to consider those relationships. We could, of course, do some plotting where we're comparing different plots, but even there, we're still thinking more about differences, right? Rather than trying to do some level of explanatory modeling. If we wanted to know, for instance, the impact that a treatment has on a health outcome, we just looked at how we could test whether that's different from zero, but we haven't looked at how we can sort of quantify that. If we wanted to see how different factors of a house are going to influence the cost of the home, again, we could ask, does it matter how many bedrooms are in the home in order to influence the selling price? But we couldn't say, how does the number of bedrooms influence the selling price of a home? If we want to know different treatments on material and how those are going to influence the durability of that material, it's the same thing, right? In all of these cases, we have some outcome that we care about, and we want to know how do different inputs influence that outcome. Whenever we want to describe these types of relationships, the most common way we're going to do it using statistics is in terms of regression models. So if we ignore statistics for just a minute and we just think about functions from our math classes, right? And we go back as far as we need to go into high school math. Sort of the most simple deterministic relationship between any two variables is going to be the straight line, right? So oftentimes you could write out y equals, say, in my math classes, it was always y equals mx plus b, right? Where m is going to be our slope, b is our intercept, and then y and x are related through some straight line. Now in stats, we're typically going to end up using Greek letters, so we'll do this instead. We'll say y is equal to beta naught plus beta 1 times x. And any linear relationship between x and y is going to be able to be written down in exactly this form, right? Y is going to be considered our response variable or the dependent variable. So y depends on x. X is going to be considered our predictor or our independent variable, so we can change X freely, right? The other way we're thinking about this in stats with the predictor and the response is that the value of X is going to predict what the value of our response is going to be. So Y is some outcome, X is the thing that we can measure that will help us predict our outcome. Beta naught is going to be our intercept, and beta 1 is going to be the slope for the line, right? The rise over the run. The simple linear regression model, the model that we're going to look at, takes this simple deterministic line and makes it into a probabilistic model, right? So instead of assuming that this is exactly the relationship, we're going to add some noise to this. And then we're going to hope that that line captures the behavior quite well. So instead of considering y and x to be fixed, we take them to both be random quantities. If we take y equals beta naught plus beta 1 times x plus epsilon, here we're thinking about y and x both as random variables, and this epsilon term is also going to be a random variable. We think about beta naught and beta 1 in exactly the same way that they were in the deterministic model, right? So it's going to be the intercept and the slope. And y is still going to be our outcome, and x is still going to be our predictor. But now we're just thinking about actually measuring a data set that's going to have our y's and our x's in it. Okay. Epsilon is what we would call a noise term. It's what actually adds some level of variability to these quantities. And the idea is that we never observe this noise term, right? It just sort of perturbs the relationship between y and x. So that relationship's no longer going to be a perfectly straight line, but instead we're going to be moving up or down from that line, depending on what epsilon is. Now, we'll make the assumption that epsilon is going to have zero mean, right? And so then if we take the expected value and we know that x equals some value of little x, and then we take the expected value of y, what we're going to find is that the expected value of y is going to be beta naught, which is just some constant, plus beta 1 times by little x, right? And so because of this, we can sort of think about the mean of the line is going to be a perfect straight line, or the mean of the relationship, and our value of epsilon is going to move us up or down from our mean, right? So the deterministic model, that simple linear model that we're all used to sort of thinking about, is going to be our model for the mean of y. And this is the idea with regression modeling, is we put a model for the mean of the process, and then any variability around the mean is just thought about as a noise term. So the randomness in this is coming from that epsilon. Now, often we're going to assume that epsilon follows a normal distribution with mean 0 and variance sigma squared, some constant variance. We don't actually need to make this assumption for most of what we're going to talk about. There are some components where it makes this an easier thing to do, but it's not strictly required. If the assumption is made, then what we know is that if we were given our value of x, y is going to follow a normal distribution with mean beta 0 plus beta 1 times x, which is what we just saw. And then because epsilon is going to be assumed to be independent of everything else, the variance is just going to be sigma squared. Okay, so it's common to assume that the expected value of epsilon is equal to 0. In fact, it's hardly even an assumption, because if the expected value of epsilon were anything other than 0, we could just think about that as being a part of our beta naught term. Okay, and so it's actually not a restrictive assumption to make. We're going to assume that epsilon is independent of x. And then if we have values of x, and we had estimates for what beta 0 and beta 1 were, then we could predict the value of y, right? If we just plug in beta 0 plus beta 1 times x, that's going to give us some prediction for the value of y, right? So we can also form predictions based on these models. So if we assumed normality, then not only could we get a point prediction, but then because we would know the distribution of that point prediction, we could also form what are known as prediction intervals around this, right? And so the assumption of normality is going to help us when we're starting to do inference about the regression model. Nothing that we look at is going to strictly require it, but it's a useful, or can be a useful, assumption for developing some of the theory around regression. So one type of plot that you'll actually be all familiar with, but that we did not look at when we were looking at plots in the early part of the course, is a scatter plot. It's probably the most common type of plot, especially if you're dealing with bivariate data. All a scatter plot is you take your bivariate data and you place it on your standard coordinate, xy coordinates, right? So you're simply just plotting down your values of y along the y-axis, your values of x along the x-axis. Each value gets a point. Scatter plots are particularly useful for seeing what the relationship between our y and our x is going to be. And because regression modeling relies on building out this relationship, we're going to use scatter plots a lot to think about, is this going to be a useful way of thinking about the linear regression here, right? So in our case, the question we're asking is, does it seem like a straight line would fit the data particularly well? Right? And so let's just look through some examples of this, right? So here we have our x values along the x-axis, our y values along the y-axis, and hopefully you can see that this would have a linear relationship fit it pretty well, right? It's obviously not perfectly on a straight line, but if you think about just variability around that line, we could put a line in here and you could see. And the idea with linear regression is we're going to estimate exactly that line that we just put on there. Okay. Now, in this case, this is obviously less good of a representation for a linear relationship, right? If you're looking at it, there's this exponential growth that we have here. And so a straight line's not going to fit very well. Now, there's nothing preventing us from putting a straight line on this graph, right? And in fact, we could draw in what the regression line would end up looking like, and we'll see how we would actually find that in the next lesson. But here, by using our scatter plot, we're going to say this isn't a very good prediction of what this relationship is. Okay. What about here? See, here's a little bit more intriguing because it kind of looks like there is no relationship, right? If we draw in the straight line, you can see the straight line, it's not that it fits badly to the data, it's just that it doesn't provide us with a lot of utility. There's a lot of variability around this line. And because of that, we have almost an exactly flat line, which if you have a flat line, it means the slope's 0. And if you think about what a 0 slope would look like in our little regression model, right? If we have y is equal to beta 0 plus beta 1 times x plus epsilon, if we take beta 1 equals 0, then we're just going to have beta 0 plus epsilon, right? If epsilon right here follows a normal distribution with mean 0 variance of sigma squared, then what that means is that y is going to follow a normal distribution with mean beta 0 variance sigma squared. And in this case, y and x don't depend on each other at all, right? So we have y is independent of x. And so what we really have here is that the flatter that line is, the closer to this independent situation we have going on. And so there's not really a relationship. And actually what we can use is we can use linear regression to test, does this relationship look like it actually exists? This is a case where we evidently are going to have a very strong linear relationship, right? If we put the line in, it's almost a perfect linear fit. Now, here we have the line is downsloping, right? So in this case, we're going to know that beta 1 is going to be less than 0 because we have a negative slope here. But this is going to be an example where the linear relationship fits very well, right? Here, we have a linear relationship, but it's not going to fit nearly as well, right? If we draw the line in, you can see, yeah, like that captures what's going on. It's not like we would need sort of a more complicated curve here, but there's just a lot of spread around that line, right? And so the idea here is that these are going to be higher variance. Epsilon's going to have a higher variance on it, and so the mean is going to be a less good prediction, but it still works, right? And so hopefully you can start to see how using the scatter plot could tell us whether the linear regression is going to be a good tool for us to use or not. And then whenever it is, we can actually start to estimate what those quantities are going to be, and we could conduct some inference around them. So those two components are going to be what we'll see in the coming lessons here. But to summarize what we looked at today, linear relationships are about the simplest relationship that we could imagine between two different variables. A linear regression takes that simple linear relationship and adds a noise term onto it, which allows us to say that it's going to be a probabilistic relationship instead. It allows us to capture real life relationships that aren't going to be perfectly linear, but are going to be close enough for us to be able to make predictions or make inferences about these relationships. We can use scatter plots to assess the linearity of our relationships. And sometimes what we're going to do is we're going to use those scatter plots to find transformations that might make the data more linear. And so we can see that in some example problems. But in particular, if you think about that example that we had here, where we had sort of this exponential relationship, and this is x, and this is y here, right? We know that this is going to look approximately like y is equal to e to the x, right? And so if you imagine taking the log of both sides here, right, then you'd have log y is going to be approximately, we'll just put a dot above this, it's going to be approximately equal to x, right? And so in this case, if we were to actually transform our data and take the log of y, that would be an approximately linear relationship, right? So the scatter plots are going to help us see, do these types of transformations seem to make sense? And if they do, we can apply them and then use the tools there. Right? So like I said, in the coming lessons, we're going to look at how we actually estimate those lines and look at how we do some inference around them. And then that's going to mark the end of the course. So I hope to see you all in these last few lessons.